Hello everyone. Let us look at how we can exploit our understanding of this anisotropy and the relation between the dielectric constant change to our electric field, which is related by our electro-optic tensor. So, let us take one material system and develop the relation between the electric field and the change in the refractive index, and also how much field is required, how much power would you need in order to create a certain amount of intensity change or phase change that you are looking at. Okay, let us look at that. So, I would like to start from our two equations, the two important equations that we had in our Parkel's discussion, which is given by the modified index ellipsoid here. So, that is the index ellipsoid with the various factors here, right. So, so let us write the factors there. So, this is one of the primary equation, and the next equation for a material, in this case for gallium arsenide, is what we are looking at, right. So, your the tensor looked 1 2 3 R41 0 0 0 0 0 0 R41 0. So, this is for the gallium arsenide as a material. Okay. So, let us take this gallium arsenide as an example, and then see how we could understand the electro-optic effect in this. So, let us take a simple waveguide made out of gallium arsenide in this case. So, the axis here are, this is x and this is z and this is y, and here the electric field, the electric field is along the propagation direction. So, this is where your electric field is, right. So, using these two equations that we have, using above equations, we can modify it and write it in this form. So, x squared n squared plus y squared n squared plus z squared n squared plus 2 R41 e of x y z plus 2 R41 e of y x z plus 2 R41 e of z x y, which is equal to 1. So, this is our index ellipsoid, right. So, this is index ellipsoid for gallium arsenide material. Okay. So, we have already seen what is the R coefficient, and also ordinary and extraordinary refractive index is something that we know of, right. So, the first three terms are independent of applied field, you can see that, right. So, those three fields are independent of the applied any field. So, these three there is no electric field involved. So, while the other 3 factors got electric field, right. So, now the field is in z direction, right. So, since the field is in z direction, right, we can actually deduce this to even simpler form. Okay. So, now there are 2 things. This is independent of this field, and then the applied field, right, applied field is along z, right. So, that is something that we know. So, because of these 2 conditions, the equation will become even simpler now. So, we can simplify this plus 2r41 E z x y equals to 1. So, this is our index modified index ellipsoid when the field is along z direction. So, that is very important. Okay. So, we are propagating light along z direction, but then your field is also along z direction. Okay. So, this is your electric field. Okay. The applied electric field is along this direction. So, this is something that we have. So, you can see here it has the cross term, the mixed term here that is present. That means the presence of an electric field along z direction is in the Cartesian coordinate system x, y and z are no longer any principal axis here. Okay. So, it is not going to be affected. All right. So, if that is the case, right, let us look at how our index ellipsoid will have when there is no field and when there is field. Okay. So, when there is no field, you will have a circular one. So, that means along x and y when the field is 0. So, when there is no field, you will not have any skewness at all. So, this is nothing but index ellipsoid. Okay. So, now when you apply a field, that is very interesting things going to happen. When the field is non-zero, the circular or the equal refractive index or the field is going to be seeing equal interaction is going to be skewed now. So, what you will see is an elliptical one with a modified x and y. So, you have x and y here. So, you will have x dash and now you have y dash. All right. So, now the coupling term can be removed, right. So, by using this diagonalization, right. So, when you do this diagonalization, when you apply a field, then you have this new coordinates or principal axis, that is x dash and y dash. Okay. And this is how it looks like, right. It rotates about 45 degree, right. So, this is how you get this elliptical from this circular, right, which is something we have seen earlier as well. Okay. So, now you can substitute this and then transform x, right. So, you need to transform from x to x dash. So, how are we doing that? So, x is nothing but x dash cos 45 degree plus y dash sin 45 degrees. Similarly, y is nothing but minus x dash sin 45 degrees plus y dash cos 45. So, this is the transformation. Okay. So, transformation of x and x dash or x from x dash. So, now we can apply this transformation to our ellipsoid here, right. So, we have written the ellipsoid equation there. So, we can apply this now the transformed form. So, now the transformed equation will be 1 by x squared minus r41 E z x dash square plus 1 by n squared plus r41 Ez y dash square plus z square n squared equal to 1. So, this is our transformed equation now, right. So, from this one, right, so we should be able to write what is our refractive index change here. Okay. So, let us draw the waveguide again that we had. So, this was x and this was z and this was y, right. So, our electric field again is along this direction. So, this was E. So, now this was x and y, right. So, we have rotated these things. So, that means your x dash here and this is y dash. Okay. So, this is the change that we have right now. And now the question is how our refractive index along this x dash and y dash is going to be, right. So, this is what we are interested in, right. So, n x dash x is equal to 1 by n squared minus r41 Ez. So, this is our refractive index or the effective index of refraction along x axis, right, and then we can do the same for y dash as well. So, what is our along the modified or transformed y is 1 by n squared plus r41 Ez. So, this is interesting. So, we have seen that the refractive index is now modified, right, based on the field that you apply to, right. So, these two are the factors that is changing our refractive index, but then whether this particular term is large or small is the question, right. So, most of the time this r41 Ez component is rather small compared to 1 by n, right. So, this r41 Ez is smaller than n squared, let us say, right. So, if this is the case, then we can invert and simplify the above equation, right. So, we can simplify this as nx dash is equal to n plus n cube by 2 r41 Ez and ny dash is nothing but n minus n cube divided by 2 r41 Ez, and finally nz dash, or in this case nz, we are not transforming it, it will just stay as n, alright. So, now we see that the principal indices here are linearly modified by the applied field. So, that is an interesting thing here. So, when we look at this, there is nothing much difference between these two. When you have an electric field, then it in the same proportion it will change along x and it will also change along y, right. So, we need to understand how this particular index change is going to affect the propagation. So far we just looked at the cross section here, right. What will be the change in the refractive index, right, is something that we have understood now, but then how is this going to affect the propagation, right. So, that is something that we should try to understand. Let us look at what happens when the light starts propagating, right. So, for that we should see a cross section of this, right. Let us take the film here, right. The light would propagate along this direction and we have y here and this is our x. So, this is basically x dash and z dash in this case, alright. So, now we have light that is propagating through this medium and it has a certain beta, So, light is propagating through this and it has certain beta, and we have our H field and then we have our E field defined here. So, now this is all fine, but then we need to apply electric field, right. So, this is your waveguide. So, we will apply an electric field here. So, you can extend these things, that means they are, you know, it looks like they are thin films, right. This is propagating along this direction. So, now this is our metal, right. So, this is our metal electrode, and here we are giving some voltage, right. So, we are applying some voltage and there is a length associated with this, there is a length L where you have this one, okay. And we are launching a mode, in this case let us say a TE mode is launched into the system, that is going through, okay. So, now the question is what will happen to this particular mode when I apply an electric field, right. So, we know what is going to happen, right. When the light is propagating through the medium, it will have a certain beta, right, and whether this beta is going to change, right. If we want that beta to change, the phase shift, right, that we expect it to change, right. So, the phase shift the delta beta is nothing but delta n x dash k naught is our change in the propagation constant. So, now what will be the phase difference that you expect, right. So, this is your propagation constant difference. What should be your phase change? It is nothing but delta beta as a function of L, right. So, now we know that this is nothing but k naught L delta n x dash, and we know this n x dash what it is here, right. So, we know what is n x dash, right. So, let us bring that n x dash here. So, this will become 2 pi over lambda L n cube r 41 E y divided by 2. So, why is E y here? Because the field is vertical, right. So, you are having a top electrode here, right, and then the field, and then you also have, let us say at the bottom, right, you have a conducting substrate here, okay. So, that is why you have the field in the transverse direction. So, that is why you have E y here, okay. So, once you have this this field here, then we know that this is the phase shift that we are getting. So, you can try to simplify this. So, once you simplify, the 2 will be gone. It is basically pi L n cube r 43 divided by lambda E y, sorry 41 by 3. So, you can see here the phase shift is directly proportional to the length that you have, okay. So, what is the how long it is. So, if you want to have a larger phase shift, you can increase the length, and you can also increase your field that you have, okay. So, for a longer device, you need lesser voltage, okay. So, to get the same amount of phase shift. So, what is required to get pi by 2 phase shift, right. So, for pi by 2 phase shift, how much is required? So, the voltage required to make pi by 2 phase shift, right, or let us say here electric field for pi by 2 phase shift is nothing but lambda over 2 to 1 by ln cube r41. All right, and this is the electric field. Okay, so this is electric field. So what is the voltage required? Voltage for pi by 2 phase shift. What is the voltage required here? So that is V pi by 2, which is given by again lambda over 2. The only difference is there will be a thickness factor T divided by ln cube r41. So this Tg is nothing but film thickness. Right. So this thickness will help you to do this. So now let us just assess this scenario here, where the phase shift is directly proportional to the length and the electric field we have. So if you want to increase your phase shift, more often that is what you are trying to do. There are two ways to do it. Right. So you can make a very long interaction, right. Or you can increase your field. So most of the time we try to keep the device power efficient and also small in size, right. So if you make it L longer, right, you will have large device. Once you have large device, then your EY goes down, the requirement for voltage goes down. So you can make it power efficient, but then the device will be larger. Then if you have enough power to dissipate, then you can have this shorter length. But another important thing is R41 here, right. So this tensor that is sitting here, in this case it is R41. In some other material it could be R13 or R33, depends on the material that you work with. For example, if you take lithium niobate for example, right. So this will be R33 or R13, depends on whether you are in ordinary or extraordinary axis. Okay. So in that case the factor here, right, the R41 or R21 factor will decide the phase shift that you get based on L and EY. So the other factor that you can choose is this R41. So R41 is the strength or the degree of the electro-optic coefficient or electro-optic strength. If the material has high electro-optic strength, then you need shorter modulators with very low power. Okay. So that is the reason why we always look for material that has larger R coefficients, right. So larger R coefficients are always preferable, and that is one of the reasons why we use lithium niobate, which is larger, and there are other materials as well, but lithium niobate is relatively widely used compared to other material for exactly this particular reason. Okay. And looking at the configuration itself, right. So there are two ways, as I mentioned, you can excite this. So let's look at the modulator configuration. So one way to look at is you could take a piece of the anisotropic material and you can apply a field in transverse. So you can have minus plus, right. So in this case your let's say this is your x and this is your z and this is your y, let's say, right. Sorry, you need to, this is your y. So in this case your voltage that you apply is nothing but Ez times, let's say, thickness T, right. And you can do something different here. So you can take the piece and then apply field between these two levels. between these two. So, you have positive and negative here, and now the field is in this way, right. In this case the field was in this direction, right. So, this is your E field, and in this case you will have a field along the length of this or along the breadth of this. So, here you have a complete length that is available to you, right. So, this is the total length you have, and in this case your voltage will be E z times L. Okay. So, you can already see which is the better configuration when it comes to the efficient use of voltage in order to get what you exploit. So, for lithium niobate in this particular configuration, for lithium niobate you could have the phase shift as follows. So, pi n cube divided by lambda R33 V L over D. So, this is your phase shift that you get when you have transverse phase modulation. So, this is for transverse phase modulation. And when you have longitudinal, so your longitudinal phase, so I can put phi t and phi L. The phi L is n cube divided by lambda R13 V. All right. So, the important thing to notice here is this n, right. So, for longitudinal component it should be n naught, and in your transverse component it will be n e. Okay. So, this is something that you should keep in mind when you are choosing the right orientation, whether it is ordinary axis aligned or extraordinary axis aligned. All right. So, that is something that you should be careful when you are choosing the right orientation. So, this is for your longitudinal . This is transverse modulator. So, so far we have looked at this modulator configurations, right. So, how to use or exploit the anisotropy that we have in the material, and we can make a thin layer of this, and either you can put the electrodes on top or you can put the electrodes on the side. It is all about exploiting your electro-optic tensor here. Okay. So, make sure that we select the right orientation of your electro-optic coefficient, so that you can exploit it, all right, and also applying the field in the right orientation. Both would work, right. It is not that one will not work than the other. So, both would work, but then the efficiencies are going to be different because of the magnitude of the R coefficients we have, and also the voltage requirement that you have, right. So, when you look at the thickness, it is basically field times thickness, but then when you have electrodes, the field times the length that you have, right. So, it have a larger or longer interaction length. So, that is the reason why when you have a longer device, the voltage requirement goes down. So, with this understanding, I think we are ready to design any modulator, any guided wave modulator based on these coefficients that we have here, but we will look at a little bit more later on in the course about exploiting these properties and how they look at. For the moment, thank you very much for listening.